No.
Oh my word.
I really
I don't even know what that is.
Exponential growth and decay.
Do we ever actually use this in real life?
Yes. Actually, I'm so glad you asked that because just wait until slide like 9.
This is
There's 9 slides.
Did you tell Will I'm not planning to be a teacher?
I attempted to. Are they not published? How is that?
Out of like all of the slides you've ever published, only one of them actually got published.
Yeah. What? Modules? Here. There.
He said that I was
Wait, who got a ticket? Sorry. Never mind. We can talk about it later. Actually? Oh.
I'm a good guy.
No, Ryan just told us this
I told my mom we could drive Annie when we were down from 31 to go to Grand Rapids and we got oh my god.
Hey, that is kind of scary. Alright, where's my pen?
This one is a lot more colorful than Spirit.
Yeah, thank you for noticing. Look, it's a new template. Isn't it cool?
I like it more.
It's kind of cool.
And it's sciencey. Yo,
Sure,
I see
yeah.
graphs. I want to get one.
Where's my pen? Literally,
Is it in that pen box?
I don't think so.
Use your Apple Watch to pee. Wait, your Apple Pen's right
Oh, there it is.
Yo,
Thanks.
Well,
Sweet. So exponential growth and decay. Now, this was something that, just like everything we've talked about so far, you spent like, let's see, you spent 1 day on growth, 1 day on decay, and maybe 1 other day on compound interest, something like that. So
I don't like
one.
that word.
So this is something that you have seen before, that you've learned before, but it's been spread out in 3 lessons. We are doing it all in one. Okay? So most of it, well, is there anything new today that you didn't know before?
Well, I
Yeah, Brian?
is that AB to the X?
AB to the X. Yep, that is our exponential growth and decay. Everything comes back to that.
Would it be like so you'd have to multiply AB before you do the exponent?
You would go B to the X. Really, I should have put not white. This should be. You should go B to the X, and then multiply that by A. But all of our exponential stuff will be in this format. What was I going to say? Oh yeah, there is 0 new learning today.
Yes.
Like all this stuff you have learned before. Now maybe you don't remember it.
Yeah.
Yeah, but there's nothing new today. So we'll see how we do. Just as a little bit or a lot of bit of a review. When we have an exponential decay function, it will look kind of like this. Okay? The big thing that we know when we have a decay function is what it says right here. That our b value will be between 0 and 1. Okay? Our b value will be between 0 and 1. Then we have decay, which makes sense, right? Because if we have y equals a times something like 1/2, it doesn't, to the x, it doesn't matter what this is. If we're multiplying by something between 0 and 1, it's going to get smaller. So our function will be decay. Now, have you guys talked about asymptotes?
Yes.
How we don't do what? We never. You guys don't know? You're
I
not
remember the
asymptote
word.
touchers. So, and with the exponential decay function, it approaches the x-axis, but it never touches it. It gets closer and 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 closer, but it never touches it. Okay? So that's something to keep in mind. It doesn't come up a whole lot in the lesson today, but we need to acknowledge that the x-axis is in asymptote. Exponential growth function. We can see down here is growing, right? And the defining way that we know that something is an exponential growth is because our b value will be
Positive.
greater than 1. So if it's decaying, our b value is less than 1 because we're multiplying by a fraction. When we multiply by a fraction, then something gets smaller. It is growing when we're multiplying by something greater than 1. Interesting. Cool. So, tell whether the function represents exponential growth or decay. Someone we haven't heard from yet today, letter A, growth or decay. Well, we've heard from Ryan and Levi, so that would knock yours out. Caleb.
They use growth.
Would be growth. Yes, very good. Oh, not growth.
Growth.
There we go. Now, we don't have a number here in front of, like our A value isn't there, so we would just assume that it's 1. Okay? What about letter B? Someone else we have not heard from yet today, Vincent. It would be decay, because we have 1/2 as our B value. Not too bad, right?
Not terrible.
Not terrible.
Physics make it harder.
Moving forward, exponential models. So this is where a little bit more of the focus is today, with real-life examples and stuff. Some real-life quantities increase or decrease by a fixed % each year. So some things, does anyone have an example of something that increases by a fixed % every year? Yes, Brian? Population by a fixed % every year. Typically, I mean, right, typically population increases. We haven't had a population decrease. So maybe population grows by 3% every year. Yes, Vic?
I don't know if it's by every year, but gas prices.
It probably, if you looked at year to year, it probably would be increasing. Anything else that we can think of?
Your salary
Like me,
Yeah,
person
because you're a
specific?
teacher. I just said it was
in general.
Yeah, I guess so. I don't know if it would exponentially grow, but
I
it
didn't
would
say it was
increase every year. What about something that would decrease? Or in what other classes have we talked about something that decreases
My
5%
grade.
every year? Your grade. Okay, grade. There we go. What else? How about like
Your amount of patience. For me particularly.
Come on, there's a couple things that we should be able to think of that decrease every year by a certain %. Specifically, I think anyone interested in chemistry or the periodic table,
Yes.
carbon, like isn't there some type of doesn't carbon get released from something that's like figure out how old it is, carbon dating?
Yeah, that's like 80%.
I don't know what the percent it is. It's still okay. Also vehicles. Every year a vehicle depreciates. So it decreases
Wouldn't that also
value.
be,
What?
wouldn't that also be humans because humans die too?
But they're
Well, the overall population, I
Every year
think,
we get closer to
typically
dying.
increases. Maybe not.
Every year life we get closer to dying.
All right, so let's look at a real life example like that. What if we use this? Here, I can tell you. The value of your car, and we're gonna have to use our calculator. So hopefully everyone got a calculator. If not,
I'm always staying strapped.
sheet off the first. The value of your car, thousands of dollars, can be approximated by the model y equals 25 times 0.85 to the t. Oh, I forgot to make one extremely important point. So here we have our. What do we think this example for this would be? Y equals a times
Increase.
Growth.
would that be growth or decay? This would be growth, right? Because we're gonna definitely be greater than. I keep saying wrong. Greater than 1 no matter what. How about this one?
Decrease.
Decay or decrease. Okay. If we said that we are growing, population is growing by 4% every year, that would mean that our rate, if we had to write that as a decimal, what would that be?
0.04.
Yeah, 0.04. Okay, so our rate would be 0.04. If we said that we were decaying by, let's say 15%.
Well, that's a lot.
Wait, but isn't that less than 1 on the left side?
On the left side, this would be 1.04.
Oh.
So it would be just barely. I mean, it would be growing fast.
Did you add
Oh, you add them.
Yep, we add the 1 to it. Our rate would be 4%, but our number in our parentheses, or our b value, would be 1.04. What about if we were decaying by 15%? What would our rate be? Yeah, 0.15. So then, what number would we see inside the parentheses?
0.85.
0.85. So one thing to be careful of, especially with decay, is that they will ask you questions like they'll ask, what is the rate of decay of this equation here at the bottom? And everyone wants to say the rate of decay is 85%.
No.
No, our rate of decay is
0.85.
15%. We're multiplying by 0.85 because that's what's left over, right? After a year, we have 0.85 left. But our rate of decay is 15%. So maybe that's a little confusing. You'll see how that comes into play in some of these examples. Back to our problem. Here's your real life application. The value of a car in thousands of dollars can be approximated by the model, y equals 25 times 0.85 to the t, where t is the number of years since the car was new. So first, is this model growth or decay?
Decay.
Okay. Identify the annual percent increase or decrease. Well, it's decrease because we know it's decay.
15%.
It would be 15%. Good, we just talked about that. And then estimate the value of the car, or estimate when the value of the car, so we're trying to find t. Estimate when the value of the car will be $8,000.
It's 25 and
So everything is in the thousands. So we would, the value of the car is y, right?
yeah.
Right? So we would say 8 equals
Oh, so it's 8. Okay.
25, because everything's in thousands. Now, we've got a problem here, because we have a variable in the exponent. Do we know how to solve anything when we have variables in the exponent? No, not yet. We will in 2 more lessons. By the end of the week we will, but we don't know how to yet.
Don't
So,
you just...
What? Do you have an idea?
Can't you just guess and check?
Well, you could guess and check. That might take a little bit of time. What would be maybe a more for sure way to figure this out?
Solve it.
Just switch your
Well, we can't solve it.
Divide by 25.
Oh, no.
Put it in your graph.
Yeah!
Yes, Levi.
Nice job. So, we want to put y equals 25 times 0.85 to the t into our y equals.
How you do that?
And we want to
You stick it in
look to see what the value of t, or what the value of x is when y equals 8. So you want to go to your table and see as close as we can to y equals 8. It won't be perfect. We want to see how much time that is.
Oh my goodness.
So put in your graph, go to your table, look at your y values, and find what the x value is when we get a y that's close to 8. I think the closest we can get is like 8.1 something. Let's see what the
Wait.
Alright. Well, how'd you put it in?
What? Let me see.
My graph is broken.
Yeah, it'll be 8.0144 will be the y value. That's as close as we can get. And the x value
There should be.
would be about 7 years. Was everyone able to put that in their y equals?
Yep. Nope.
All of my things are 25.
What? Or what?
All of my numbers are 25.
25.
Yeah, you put it in.
What?
Picture table says.
No, that's what mine was at first. You have to put x, like to the x.
Yeah, you can just put it to the x.
Oh.
Yeah, don't worry, put it to the t.
How is
And then
Guys, I figured that out for Ryan.
Yep.
there you go.
I
That's
actually
the
figured it out
the x
myself.
value.
I just lied to you.
Yeah.
Yeah.
I have to take this moment before I get it.
How's your bracket doing?
Wait, why is
There
this
you
perfect?
Turn these together. You plug that in the y equals.
You can go busted.
Yeah, Greg.
Go check out my mic.
Who did that? I don't know. It's the we're on the how it was.
That is wrong.
No, we use them in second hour. So second hour is gonna get. I know exactly what it was.
Wait, hold on.
There were 2 guys in the back of the class that were just plus the ethanol class and looking, and now I know why. Nice.
Wait, what?
No, it doesn't matter.
What?
Anyway, when we put this in our calculator, we look at our table, and we can see that our closest x value, or our closest y value to 8 is 8.0144 or something like that.
Yeah.
And that would be when x or when t equals 7. So we would say that estimate when the value of the car will be $8,000. We would say after 7 years.
Oh, we
Okay.
Wait, so it would be t equals 7?
Well, you don't put t in for your variable, you just put x.
I gotta wait
So t, this is approximately or about.
Is that
It's about 7. About 7 years. We'll look at another example. In 2000, the world population was 6.09 billion. Someone said population earlier. Good job. During the next 13 years, the world population increased by about 1.18% each year. Write exponential growth model giving the population t years after 2000. Estimate the world population in 2005. So 2 parts to part A. First, we need to write an equation. Right? It has to be in this form. Now, what would our A value be? What would our A value be?
13.
Wouldn't be 13. That's our time, right?
6.09.
Yeah, it would be 6.09. That A value, we'll talk about it as our principal later. That's always our starting amount. Okay? That's our starting amount. Now in our parentheses, we are increasing by 1.18% each year. So what would we put in our parentheses? What was that? I see where you're coming from. Not
1.18?
What?
1.18 because it can't.
So remember, when we write something with exponential growth, 1 plus our rate to the time.
So 1 plus 0.18.
So 1 plus 0.0118,
118.
right? Because we need to write that percent as a decimal. So our rate is 1.18%.
That's what I said.
So when we write it as a decimal, so plug into our formula here. That's how we would write it. Now we can simplify. Do we see that? What do we see why we can't just put why we can't just put that percent in there? 1.18. Because that is our rate. We need to write our rate as a decimal. And then 1 plus our rate. And then I put 2 to the t. I mean, that would just be for time. If you put 2 to the x and when you graph it, you would put 2 to the x. It doesn't make a difference. So, the first part, we wrote, let's see, write an exponential growth model. Boom, we did it. Estimate the world population in 2005. What would we do for that, Ryan?
Don't you just look at your y or your table and then you go to 5?
Yes, yep. You can do that. Essentially what we would do by looking at our table would be plug 5 in for t.
Yeah.
Right? It says that we're starting out in 2000 and it wants to know the population in 2005. So we're looking at 5 years down the road. So when t equals 5. And one of the ladies in the back row, when t equals 5, what would our population about be? One of the ladies in the back row. You can put 5 in for t, or throw that in your y equals and look at that table. 6.45. Perfect. I agree. 6.45.
7.
So approximately 6.45 billion people would, I mean, if this model is correct, approximately 6.45 billion people would be in the world in 2005. Part B is just like what we did in this example, so we're going to move past that. One last idea that we need to look at, and then one more example.
Hey, you didn't do part B.
Yeah, he just.
What did I just say about part B?
It's the same thing as the other that we just did.
Yes. Yes.
Well, yeah, it'd be 2000. Bingo.
Okay, compound interest. Here's another real life application. See, some of you might think that it's really fun to estimate your world population, which all the power to you. But other people might want to say, how much am I going to have in my bank account down the road? So that's where we use compound interest.
Yo.
Compound interest. It's in the same format. I mean, this is the same as y equals a. I mean, all of this is our b, and then all of this is our x. So it's still in that exponential format. We just have, it's a little more complex for how we find our b and find our x. Find our exponent. There's a little more to it. Does this look familiar?
Yeah. Yes. I do. I remember doing this.
No, I'm not. You're like, nope, never seen it ever in my life.
In Mrs. Hill's class.
Yo, I don't remember anything in that class.
Yeah. So get this formula down in your notes. I would also get each of these terms. And then we look at one example. You guys haven't done anything with logarithms yet, have you?
Logarithm?
I think we did one.
That's what we're learning about this week. Logarithms are cool. We'll bring on down now along those sides. Also, will this to this equals that number anyway. We'll go like 10 more seconds to get moving right down.
That's really
Alright, so, hey, what we end up with, our ending amount. How much we'll have in the account, in bank account is the classic example. How much we'll have in the bank account after 10 years, 15 years, whatever. Our principal is our starting amount. So they would say something like, you open a bank account in 2000 with, in the year 2000 with $5,000, and that would be your principal at $5,000. 1 plus, because we have exponential growth, so it has to be greater than 1. Our rate would be something like your principal increases 4% every year, okay? Or 4% annually. Now, this N is where people get confused a lot of times. You'll hear words like your interest is compounded quarterly. How many times a year is quarterly?
4.
What about semi-annually?
2.
Good. You'll hear some different terms like that, and that is where this N comes into play. If we are compounded quarterly, our N value would be 4. If we are compounded quarterly. So however many times a year our interest is compounded would be that N value. We need to divide our rate by it. Again, that N value appears up here in the exponent, and then T is our variable most of the time. So T would be time, as always. Let's look at an example. Not as complex. You deposit $9,000 in an account. What would that $9,000 be?
9.
Well, okay. Yes. Our principal. Thank you, Caleb. 1 plus. An account that pays 1.46 annual interest. So if it pays 1.46% annual interest, what would our rate be?
0, 1, 4. Over 1.
Annual interest.
1.
Find the balance after 3 years. So there's our time, 3 years. When the interest is compounded
Quarterly.
quarterly. So what would we be dividing by? 4, because we're compounded quarterly. That's how many times a year is compounded? 4 times. Our 4 shows up twice. So if, well, I guess we'll start here. If they asked us to write an equation, here would be our equation. Now we could simplify that. What is 0.0146 divided by 4? What you got?
0.00365.
Yeah? So this would be our equation all the way simplified. Now what they want in this problem is find a balance after 3 years. So when t equals 3. Yep, so in our exponent we would have 12. So y equals 9,000. And we can just plug that into our calculator.
9,400. How many did you get to do? $9,402. That's right.
Nice, great.
Any sense? Grace, are there any sense?
So basically, in 3 years, we gained $400.
Yep, just from your interest. Just because the bank can use your money to loan it to other people.
Exactly. And then they pay you back. Sometimes.
What's the bank's
How are we feeling about this stuff? Is it, do we remember enough that this is just a refresher and we're good? Or do we not remember anything and we're a little bit lost?
Refresh.
Don't remember anything but we're not lost. Okay. I'm happy with that.
I remember doing this.
I do have a class